Machines have become an integral part of our lives, and therefore a familiarity with them is essential for every student. In an age of machines, we need to focus on becoming familiar with a large variety of relevant examples of simple machines and seeking opportunities to analyze and identify simple machines. A machine, like a bicycle, has a combination of levers and gears. A mechanical juicer has a lever and a screw, and this vegetable cutter has a lever and a wedge. The crowbar, wheelbarrow, or the tongs have been around with us for a long time. They help us do our work with a minimum of effort. Such appliances are called levers. A lever is a rigid body which is pivoted about an axis called the fulcrum. An effort is applied at one point to move the load applied at some other point. Using a crowbar, a heavy load positioned at one end is lifted by applying a downward push, the effort, at the other end. The crowbar is pivoted and moves about this pivot. The point is called the turning point or the fulcrum. Here are some more examples of levers. Notice that in all these cases, the fulcrum lies between the load and the effort. Levers in which the fulcrum lies between the load and effort are called first-order levers. Simple machines like scissors, pucker, and crowbar are levers of the first order. Observe this wheelbarrow. Notice that the load lies between the effort applied at the handle and the fulcrum is at the other end at the wheel. Let us now look at some more examples of this type of lever. Levers in which the load lies between the fulcrum and the effort are called second-order levers. We have used a pair of tongs to lift rotis, ice cubes, or sugar cubes, or coal cinders. Observe these examples of levers. levers in which we apply the effort at the center and the load and fulcrum lie at the ends are known as third-order levers. We have seen that a lever is a rigid body which is pivoted about an axis called the fulcrum. An effort is applied at one point to move the load applied at some other point. Watch this balance. When the balance is balanced, the force acting on the weights is equal to the force acting on the object being weighed. Now, what would happen if we moved the fulcrum? In order to restore the balance, we may increase the load. Or, if the fulcrum was moved the other way, we may increase the effort. Is there any other way of restoring the balance? What we have established is that the arms of the lever also have a role to play. The balance is restored when the moments of the force are equal. This also means that the shopkeeper can balance a smaller quantity by a larger weight. He derives an advantage. We define a ratio of these moments as the mechanical advantage. In the case of a balance, the fulcrum is exactly in the middle and the moments are equal. The mechanical advantage is 1. When the effort is greater than the load or the effort arm is smaller, the mechanical advantage is less than 1. You then put in a greater effort. But if the effort appears small or the effort arm greater, the mechanical advantage is greater than 1. You then have to put in lesser effort to do the work. So the next time you want to make a big effort, don't go to the gym. Just give yourself